Hey guys, it's Anil. In this session, we would study and understand the behavior of a material under the action of forces. And we are pretty concerned about the solid materials, rather liquids and gaseous. If someone hangs an object from the rope, it is not the weight of the object which determines whether the rope will fail, but it is the weight of the object divided by the rope cross-sectional area, a fact noted by Galileo in 16th century. In a moment, we define this quantity as stress. To begin with, I have a rectangular bar. Say we are applying equal and opposite force. In former case, the forces are trying to stretch the bar. In later case, the forces are trying to shorten the bar. The former case, we call the bar is under tension, whereas in later case, we call the bar is under compression. Though it looks very simple loading and simple shape, but there are many practical application where you can categorize under simple tension and compression. Starting with the ceiling fan, the ceiling rod would be under tension because of the weight of the fan. Whereas coming onto the column of a bridge, it would be under compression. On similar lines, you can assume the rope bridge as well as the towing rod during the towing of vehicle. Whereas towing rod would be under tension. Let's move on to the definition of stress. Take again the rectangular bar and apply the force on one end. We draw a free body diagram for that by isolating the bar from the elements that are holding it by replacing with the forces. Here is the free body diagram. Let's look at the microscopic structure. You can see here atoms and molecules are connected by some means. The moment you are trying to apply the external force, there would be resistance set up within the body in the form of interatomic and intermolecular forces, which would balance the applied force. We call this as the condition of equilibrium. And let's cut a section at A and draw the free body diagram again. You can see here on one side we have external forces and the other side we have internal resistance forces. If you sum up all the internal resistance forces, that would be equal to the applied force. You already know this is the condition of equilibrium. If you look at the cut area, the internal forces almost resembles like pressure. On similar lines, the way we define pressure, we define stress as the internal resistance force over the area. Mathematically, we can define stress sigma as the internal resisting force over the area, and which is equal to F by A. And the units for the stress is Newton per meter square. We call this as Pascal, or sometimes we use megapascal or gigapascal, depends on the convenience. Moving on to strain, let's again take the same rectangular bar. Again we are applying force F on one end. Due to this force, bar experiences a stretching, and the total stretching the bar experiences is delta L, and L will be the original length. We define strain as change in length over the original length, or deformation over the original length. Epsilon is equal to delta L over L, and which is the dimensionless quantity. Moving on to strength, which is the property of the material, we can define strength as the capacity of an object to withstand the applied load or force.